you wonderful physics kids. Mr. Johansson here. Today we're going to be looking at how to do cliff problems. Cliff problems. So let's set up what the idea on a cliff problem is gonna look like here. So I can have it all written out. I could say an object is thrown horizontally, this way, off of a cliff, 78 meters tall. How far away from the base will it land? Well, how are you gonna do that? It's thrown horizontally. Let's look at a free body diagram, shall we? Always, if you're wondering, look at a free body diagram because it kind of gives you what's happening to it. So once the object is thrown, not while it's being thrown, but once it's thrown, and it leaves there, I'll do a circle for a free body diagram today. What are the forces acting on it? Does it still have a force pushing it? No, you're not throwing it anymore. You're done throwing it. So is there still a force pushing it? No. Generally, we're accepting that the velocity is small enough so the force of air friction is very tiny, negligible, we can throw it out. So are there any forces in that direction? Are there any vertical forces? I'm sorry, are there any horizontal forces? No. Are there any vertical forces on it? Well, the object still has its weight, correct? So the vertical force of weight is acting on it. Does it have any forces that are keeping it up? No. So it's purely its weight, which means whatever's happening in the horizontal direction, that's unaccelerated. What's ever happening in the vertical direction is accelerated. Now, ask yourself, what's going to stop this object? Well, when it hits the ground, right? When it hits the ground, it's going to stop. So what we need to know, because we have the height of the cliff is 78 meters, is that going to govern how long it'll take to hit the ground? However many seconds it'll take till it hits the ground, and every one of those seconds, the object is still moving at this 12 meters per second horizontal rate. Okay, so we have to separate the givens into vertical and horizontal. The reason? We're going to need the vertical givens to find out the time it will take till the object stops moving. The vertical givens determine that. And whatever time that is, we just multiply by the constant horizontal velocity, and we got it. So the givens set up in sort of a new way. The givens now, we write the word givens, but then we put a V after it, indicating that every given here is a vertical, not a horizontal given. All right, so let's think about this. Yeah, we know the distance is 78 meters. Great. Well, is it under acceleration due to gravity vertically? You bet. This is an accelerated thing, so we're at 9.8 meters per second squared. Now we understand, we're going down, so we make that negative. Acceleration due to gravity is negative. What's the time have to be? Can it hit the ground several seconds before you drop it or throw it? No, so the time has got to be positive in any case. But having both of these negative will solve that problem. Yeah, so I'm looking for the time, and you can see D, A, and T. I don't have enough to solve this problem yet, so I must be missing something. What's my phantom given here? You got to think about this. In the vertical direction, what is my initial velocity? Right. My initial velocity vertically, up and down, is 0 meters per second. That's a key understanding. All right, so when I look at D, A, T, and V, or V sub I, what do I have for a formula here? Most popular one ever. D equals VIT plus 1/2 AT squared, right? Our old friend. So for this formula, what happens to the VIT term? All right, well, we say VI equals 0 meters per second. Don't forget units. Therefore, D equals 1/2 AT squared. Now we have to solve that for T. Hope that's not too big a deal anymore. So D equals 1/2 AT squared. How about 2D, that gets rid of the 1/2, over A, all of that is going to equal T squared. So if I take the square root of this, that equals T. I hope that's a relatively smooth derivation for you. It's not that big a deal. We've been doing this. So for S and S, T equals square root of 2D over A. In any problem like that, remember the biggest issue you might have is forgetting to take the square root. Can we come up with how many seconds a 78-meter drop is going to take? If you've been doing drop problems, you shouldn't have much trouble with that. How about a 3-second drop problem? Starts at 0, ends at 30, average 15 for 3 seconds, gives you 45 meters. 78 meters, more than that. So it's more than 3 seconds. How about 4-second drop problem? Starts at 0, ends at 40, average 20 times 4 seconds gives you 80. Slightly more than that. So this is just slightly under 4 seconds. Got it? So our drop problems, once again, are wonderful to do. And if it's just about 4 seconds, we're multiplying that 4 seconds by 12 meters per second every single second. You can see you're going to be about 48 meters away. You can do all that in your head really quickly, and you're going to be pretty close. You've got to learn to do it properly, though. All right, so we have t equals square root of 2 times 78 meters over 9.8 meters per second squared. Oh, let me make these negative. Now you see the negatives cancel out there, so it is kind of just a bookkeeping issue. What does my time equal there? All right. Well, I have 2 times 78 divided by 9.8. I have 15.9 seconds. Is that correct? Could it be correct? Falling 80 meters, about 80 meters in 15 seconds? You know better than that. That cannot be correct. What did I forget to do? Hit the square root button. Once you hit the square root button, now you have 3.99 seconds. Does that sound right? Yeah, sounds just right. 3.99 seconds. And now we do givens, but these are givens horizontal. Nice and simple givens horizontal. What do we have? Well, we have our time equals 3.99 seconds. Our velocity is 12 meters per second. And then we're looking for distance. So the formula then, velocity equals distance over time. Distance equals velocity times time. Again, I hope I'm not going too fast for you, but we've been over this. S and S, D equals V times T equals 12 meters per second times 3.99 seconds. What does all that equal? Times 12 equals 47.9 meters. Like we said, just about 48 meters. That's how you do a cliff problem. You find out how long it's going to take to drop to the bottom, all right, by doing a vertical set of givens. Key with vertical set of givens is your VI is 0 meters per second. That's your vertical velocity. Your horizontal velocity is completely independent of that. This gets to the old great physics question. If I have a bullet and I have a gun here, and they're both identical bullets, but one is in a gun, and it's perfectly flat where I am, and I drop the bullet and shoot the gun at the same time, which of those bullets hits the ground first? Well, you can fuss at this all you want. Why don't you make a free body diagram of what those bullets are experiencing? After the bullet emerges from the gun, what are the forces on it? What are the forces on the bullet? The force on the bullet, here, look at that, I'm even drawing a bullet. The force on the bullet is purely its weight, even though it has a velocity. And we know it's going to have a force of friction slowing it down, but it's minor because it's a small object with good inertia and it cuts through that air nicely. So we're ignoring the force of friction right now. So what other forces are acting on it? It's just its weight. How about the bullet that has no velocity? Also, its weight. And as counterintuitive as this sounds, both bullets hit the ground at exactly the same moment. The point being, vector quantities in different directions are completely independent of each other. If you shoot a bullet, it does not change how fast it's dropping to Earth. Now, if you're saying, no, a shot bullet somehow has lift, how would it have lift? Lift would be because of its shape. If its shape somehow can get it to lift up in the air, the other thing about bullets will throw you completely off because that bullet is spinning. to make it more accurate, we spin the bullet. And it makes it very hard for that bullet to tip in any direction except go forward exactly straight. So if it has lift because of shape, as soon as we spin it, it's going to be lifting in all directions. So that wouldn't work at all. So there is no other force on it. It just is falling due to gravity. Now we are projecting it forward mighty fast. That's what makes it seem like it hovers in the air a little bit. It certainly doesn't. It does not hover in the air even one nudge as much as a bullet just being held. They would fall exactly at the same rate. So vector quantities are completely independent there. That's cliff problems and a little bit more. Thanks for watching.